You ever woken up, looked at yourself in the mirror and said, am I a triangle? You may be suffering from trigonometric identities. Just kidding, it's not a real thing. It's more math. It's our last video. You're done after this, except you write a test. So you're not even close to done. You got to review everything and it's awful. But hey, it's our last content. And you're on the home stretch, so we saved the hardest for last, just for you. This video, we're going to be going over what is an identity, how do we prove an identity, how do we, test values in an identity, how do we do all kinds of nice, cool things like solving equations with identities. We're really going to identify with the math here. Before I go further, what am I even talking about? Well, an identity is an equality relating one expression to another. So an example is if I have, a triangle. Let's draw a triangle. I'm going to use lines here for triangles. Oops. And I'm going to ask you to pretend along with me that this is, in fact, a right angle triangle. So if I have an angle here that's given to me, we'll call this angle alpha just for fun. And then I have this side X I'm trying to decide. I could say that, well, let's call this Y and Z. How about two? I could say that X could be solved by doing X is equal to the square root of Z squared minus Y squared. And that's just because of our Pythagorean theorem, right? So A squared plus B squared equals C squared. So B is equal to the square root of C squared minus A squared. I could also say that X is equal to, well, what's this one equal to? This would be equal to Y tan alpha. Okay, and so I could say then if this is a way of finding X, and then this is another way of finding X, I could say that Y tan alpha must then be equal to the square root of Z squared minus Y squared. Hey, look, two things that look pretty different, but in the context of this triangle, we're looking at the same thing. They are equal expressions. And we're not going to be talking about such specific cases. We're going to be talking about expressions that are universally identities, right? And you'll see more what I mean when we actually go into them. Before we go on to proving them, we'll have a little bit of time to experiment with them. In this video, I'm not going to spend any time proving all of these. I'm actually just going to kind of pick and choose through a number of them. And you should right now, if you don't already have a formula sheet for Math 30-1, you should look up Math 30-1 data sheet or formula sheet. Data sheet, if you type that one in, it's the same thing as a formula sheet, but you're more likely to get the official Math 30-1 diploma given data sheet. That's what you're going to get on your diploma. And on your diploma, if you take a peek at your data sheet, you'll see just what I mean. Oh, awkward. There's that. Okay, so let's look this up. Math 30-1 formula sheet. Sure, we'll do formula sheet. Here we go. Tutor Calgary. How about that? Okay, this is the Math 30-1 formula sheet. I don't need this, but I can't remember how to close it. Whatever. Look at our right side here. It's all trigonometry, and you hopefully recognize these two formulae. And maybe this one. We don't spend a lot of time in my class on it, but you've probably seen it before. And maybe our reciprocal identities. But everything that I've just highlighted, these are trigonometric identities. Half your formula sheet is dedicated to trigonometric identities. So that should be kind of a no-brainer that you're going to need that formula sheet if you want to be successful with this section. What are we going to use that formula sheet for most heavily is proofs. Now, a proof is something that is very, very integral to math and like working with math, but we don't really cover a lot in the Albertan curriculum. And that proof is a method for showing that a statement is true, or in this case, that an equality is indeed truly equal, is truly an identity. And when I say an algebraic method, that is for us particularly. There are other ways we can do this. We can use deductive reasoning as well. But in this case, we're using an algebraic method for showing that an equality that's given to us is actually truly equal, which means it is an identity. So let's go ahead and let's talk about some of these identities. The first is that we have our reciprocal identities. Now, remember on our formula sheet, it wasn't written quite the same way. We could say that tangent has the reciprocal ratio cotangent theta, or I could write it this way. I could say cotangent theta is equal to 1 over tangent theta. Okay, and the same for all of these. That's on your formula sheet. That's given to us. And this is an identity, sure, but it's kind of like a contrived identity. We're just saying, okay, here's what these ratios are: cotangent, cosecant, and secant. They're just a way for us to represent the ratios that we usually use, but in a reciprocal form. Okay, so that was fun. We can skip the rest of that page. So next up, we've got our quotient identities, tan x and cotangent x. Awkwardly, I guess I'm going to go back and forth between using x and theta, but it doesn't matter, of course, right? Just ensure that your variable is consistent. Okay, so if I have tan x, our quotient identity, excuse me, is saying tan x is equal to sine x over cosine x. So here's what we're going to do. We're going to do a proof of that one, and then hopefully you'll be fine with me if I skip the other one. So let's go ahead and do a proof here. So anytime I'm doing a proof, and we'll do more rigorous looking at this later in the video, I'm going to set up kind of like a left-hand side and a right-hand side of my equality, because there is, in fact, a left and right-hand side. So I'm going to manipulate my right-hand side and my left-hand side and make it so that they're equal to each other. So what is tangent of x? Well, remember, tan of x is equal to our y value over our x value. Okay, so we can say then that, oops, sorry, don't forget your x. Okay, we've got y over x. Now, maybe it would be better if I used a different variable than x in my equation, because like x and x, these are different meanings for x, but awkward. Okay, what's sine over x? Well, sine over x is equal to y over r, and cosine of x is equal to x over r. Again, not the x's that are the same. Okay, so that means this is equal to y over r over x over r. If we do the math here, don't cancel with green. Our r's cancel out. And so, yeah, this is equal to y over x. And so our two sides are exactly identical. Yay, that proves that they are truly the same thing. Note, one thing I don't do here is I don't just plug a value in and say, hey, look, it came up with the same thing. They must be equal. No, I need to prove that they are actually equal by algebraically coming down to the exact same thing. And at the end, I might put this: left-hand side is equal to right-hand side, as kind of like a woohoo, I did it. There, I proved it. You can prove cotangent x is equal to cos x sine x on your own. Next up is our Pythagorean identities. In the space below, we'll go over, maybe we'll go over one of them here. So I'm going to go ahead and we'll do triangle here. So this is a right angle triangle. Keep in mind that if we're using our unit circle, let's say this is a triangle on our Cartesian plane, our radius is equal to 1, and then our y value and our x value, right, given an angle theta. So if I have this angle theta, if I want to find y, that is y is going to be equal to our value for sine theta. And remember, technically it's y over r, but r is 1, so y is equal to sine theta. X in this case is equal to cosine theta, using the same logic. Sorry, that pen just slipped or something. So I can say then that x here is equal to cos theta, given our circle, and y is equal to sine theta. And then I can say, well, why not I do the Pythagorean theorem with that? So I get this: sine squared theta, remember that square is like on the whole thing here, plus cosine squared theta is equal to 1 squared, which is just 1. And that is the first of our Pythagorean identities. Let's take a look at the next two. Our next two are 1 plus tan squared x is equal to secant squared x, and cotangent squared x plus 1, which actually is written differently on your formula sheet, is equal to cosecant squared x. In this video, I'm not going to go over those guys because I just want to make sure we can get to the stuff that you're actually going to be tested on in your diploma. You can just choose to believe me, or you can look this up. Google a video where someone cares more about you and will actually show you. Okay. So let's use some of these. Before we do that, we're going to want to think about what are some values that are going to be non-permissible. So remember, just like in the real world, in the math world, you can't divide by zero. So trigonometry has the same set of rules. We got to make sure that we're not dividing by zero at any point. So we're going to look at all of our ratios here, and particularly if we have a quotient, we'll make sure our bottom isn't something that is opening zero. There we go. And then like something like tangent has its own limits to it. So we'll just double check it. Okay, so let's do one piece at a time here. So secant x is equal to 1 over cosine theta, or secant theta equals this. So we can say then that cos theta cannot equal 0. And when does cos theta equal 0? Well, it's equal to 0 at pi over 2 and 3 pi over 2. So these are non-permissible values because they'll create that. Now, they're asking kind of in general form here, I guess. So we could say either of these, or honestly, actually, here's a cheeky way I could save it. I could say plus or minus pi n, where n's an element of our natural number group. Okay, so that works. Now let's look at tangent. Tangent theta, you're not allowed to put pi over 2 again. So that actually kind of double does this. And then let's look at sine. So we're saying then that sine theta also cannot equal 0, which means that we can also not have 0 plus or minus pi n, where n is an element of the natural numbers. Oops, want to put that. Okay. Final, perhaps spicy answer I could put is 0 plus minus pi over 2 n plus, no, I don't need it plus, where n is an element of our natural number family, because that kind of encapsulates both of them. Cool. How about this one? And by the way, these numbers beside them, those are just the textbook pages that they're from. Tan x, well, we know that we can't have tan x equal to 0, and we also can't have tan x equal to, well, it's got a non-permissible value of its own. So let's look again at secant x. So secant x, we know pi over 2 plus minus pi n, where n is an element of the natural numbers. That's non-permissible values. And then for tangent, we know that tan also cannot equal to 0. So what's the case when that'll happen? Tangent is going to be equal to 0 when the value for our y coordinate is 0. And so that means that we can't have 0 plus or minus pi n, where n is an element of the natural numbers. Okay, and so that means we actually end up with the exact same answer. Not allowed. Okay, so one thing that we can try and do is we can do a verification. Now, a verification is not a proof. Remember earlier, I said you can't just start plugging values in and saying, look, I got the same answer on both sides. I've proved it. No, it's a verification. It's not a proof. You've just said that at this specific value, it does work. That's it. Not good enough for full marks on a diploma style question, but it might be a good idea to add it in after you've done your proof and say, hey, look, I'm going to verify at this value, blah, blah, blah. So what we're going to do is we're going to test the verification here. Here are two of our identities. We'll verify them at some specific points. Okay, so let's start with this. Cotangent x is equal to cos x over sine x at 45 degrees. Okay, well, 45 degrees for tangent. Actually, maybe I'll rewrite this a little first. So cotangent x is tan x as a reciprocal, and this is equal to then at 45 degrees, that is 1 over 1. Well, let's write the whole thing first. So there we go. So at 45 degrees, tangent is a ratio of 1. So this is going to be 1 on this side. Okay. And at 45 degrees, cosine x is root 2 over 2. And that's divided by, again, root 2 over 2. Okay, and that cancels out to be 1, so that does verify. How about at pi over 6? Notice we're doing two different places here. That might be nice. So we get 1 over tangent at pi over 6. That's going to be our y value, which is 1/2, divided by our x value, which is root 3 over 2. So that's 1 over root 3. And 1 divided by 1 over root 3 is root 3. Okay, on our left-hand side, cosine x is going to be root 3 over 2, and sine x is going to be 1 over 2. And that actually also cancels out to give us root 3. So that verified. Cool. So both of our verifications are good. One thing, hopefully, that you're recognizing here is we've kind of taken the unit circle training wheels off. You don't need to do this as fast as I do, obviously, right? You get 6 hours for your diploma. You're going to be like losing your mind if you stay for the whole 6 hours. That's how long it feels. Like you're trapped in some sort of math dungeon. But look at how easy that question was because I've got my unit circle memorized, right? I'm not giving it to you on your diploma. You're not given it. So you have to like either create it or memorize it. But the more confident you are with your unit circle, this was easy, right? So just, food for thought. Okay, this one's going to be a little silly for our first one. So we've got x equals 3 pi over 4. So on our left-hand side, 3 pi over 4, that's a pi over 4, or like our denominator is 4. And so that means we have a tangent ratio that's either going to be +1 or -1. So if I square it, it doesn't matter, it's +1. So our left-hand side is equal to 2. 1 plus 1 is 2. There you go. There's a math fact for you. 1 plus 1 does, in fact, equal 2. On the other hand, we have secant squared x. So that's going to be equal to 1 over secant fractions with cosine 3 pi over 4 squared. Okay, so let's think about what we're going to get here. Okay, so 3 pi over 4, that's our ratio is going to be negative root 2 over 2. So if I have negative root 2 over 2 on my bottom, it's going to be 2 divided by root 2. And it's negative still, squared. And so that is equal to 4 over 2, which is equal to 2. There we go. We verified it. Nice. So let's keep rocking and rolling here. There are proofs for all these, but all I can tell you is that they're not worth learning at the level we're going to be working at. So you're just going to have to remember these 3 groups of identities. And if you don't remember them, I've got great news. They're in your formula sheet. Just look at the thing. They're there. So we've got the sum, where you have 2 angles in a ratio, sine, cosine, and tan. You've got the difference. Yeah, you get it. And then we have these double angle identities. And please keep in mind that sine and tan both have only 1, but cosine 2a has 3 ways you could write it. Ooh, right? Yeah. So anyways, that's cool for us. Let's just have looked at those together. Good for us. I think we're gonna skip. Yeah, I think we're gonna skip this one because primarily like that's this, right? That's there. But we kind of want to get into just the values here. I think we'll also skip these two. Yeah, for now. Let's go on to actually proving these things, okay? So for proofs, remember, a proof is not a verification. A proof is an algebraic demonstration that both sides truly are equivalent, whereas verification is just checking at a specific value. So you don't want to do a verification under the assumption that it's going to be effective enough as a proof. The next thing is that we're going to go over some helpful hints for how to attack these sorts of things. And I'm going to be honest, there's no like way I can say, look, just do this and it'll work. because one of the best analogies I've heard on this is that it's kind of like a Rubik's Cube, right? There's some ways you know that you can use this technique or that technique, but I can't give you a Rubik's Cube and you know, okay, I go 3 turns left, 1 turn right, and then remember it's got 3 dimensions, so it blah, right? There are some general ideas that are helpful. Page 313, if you have your textbook, go ahead and grab it. I'll read these out in a second. But generally speaking, you are going to have to go through this almost like a puzzle, right? So to help you with that, I have in fact done exactly 0 prep for this video up to this point. And we're going to do these, we're going to solve these together. So I'm going to go ahead and pull out my formula sheet. I'm going to have that handy. And I'm going to go through this just as blind as you are right now. And we're going to find our answers together. And I'm going to tell you how I used my strategies. So before we go any further, this is what it says on page 313. It says some strategies that may help you prove identities include use known identities to make substitutions. That's obvious, hopefully. If quadratics are present, the Pythagorean identity or one of its alternate forms can often be used. So that's helpful, right? If you see a quadratic or if you see something squared, think about the Pythagorean identities. Rewrite the expression using sine and cosine only. Put a big star beside that because those ones are really, really helpful. If you can see it written as sine or cosine, you can usually kind of see the link between left and right-hand side. Multiply the numerator and the denominator by the conjugate of an expression. That's a cool one. Or factor to simplify expressions. Lots we can do to try and make this work for ourselves. So let's try a couple of these. Now, trigonometric identities are extremely difficult for me to just snap my fingers and create. So I stole all these from the textbook. These all have matching examples with them, and they're around this page 313. So you can find these examples again if you want. But in general, I would say it is very, very helpful to look through your textbook and check out all the examples in your returns. And then I've left all the questions at the check and reflect or whatever they call them in this book for you to do yourself. I'm also going to have tons of extra resources in this because the more you do this, the better you're going to get at it and the less insane it's going to feel. Okay, so our first one is prove that sine 2x over cosine 2x plus 1 is equal to tan x. Oof. Okay, well, let's start with this. I'm going to go ahead and put down that 2 sine x cos x. Actually, sorry, let me restart this. I'm going to set up a left and a right-hand side. I see sine 2x, and I'm going to start by using my double angle identity. And I know that that is 2 sine theta cos theta. Oh, actually, they use alpha, not theta, but we're using x. So I'll go back and use x. Sine x cos x. Okay, and so that's on my formula sheet. And on the bottom here, I've got cos 2x plus 1. So I'm going to put that plus 1. And then I know I've got more than one way to use my cos 2, right, x, my double angle identity for cosine. So what I'm thinking about then is what's going to be helpful on my right-hand side? Well, tan x is equal to sine x over cos x. And so the things I kind of see that are a problem for me are this 1 here, and there's a cosine x on top. So if I can cancel a cosine x on top, then I'm sort of closer to it. And if I can get rid of this 1 on the bottom, that's nice too. Here's what I came up with. What if I do 2 cosine squared x minus 1? That's one of our double angle identities for cosine 2x. And look what happens. We have -1 and +1 cancel out. Then we have our 2's cancel out. And I have cosine squared on bottom in my denominator. My numerator has cosine x. So I can just cancel that out. And that leaves me with this, that sine x is equal to cosine x. And that shows that my left-hand side is equal to my right-hand side. And la-di-do, I did it. That's the sound of people celebrating in math, la-di-do. So that one looked nice, but then things get uglier, okay? Prove that 1 over 1 plus sine x is equal to secant x minus sine x times secant x over cosine x. Ooh, well, that sucks. Or does it? Let's play around with it a little bit. Another kind of hint that I find is helpful is that this guy here, like, what am I going to do with this? I could think about multiplying by my reciprocal here. Yeah, that might be helpful. But there's not a ton of stuff I can do other than that. And when you look at something like this, if you see a difference on a denominator, that's kind of telling me that I should work with my reciprocal. Or by my conjugate, sorry, multiply top and bottom by my conjugate. But on the other side, I got a ton going on, so maybe I'll deal with that first. So on my right-hand side, I can factor out secant x. So I can say that secant x is multiplying 1 minus sine x over cos x. And this should be really damning that I want to do that multiply by my conjugate, because this is the conjugate of 1 plus sine x. So let's go ahead and do that. We'll multiply both top and bottom by 1 minus sine x. So I'm going to get 1 minus sine x over 1 squared minus sine squared x. Yes, I put 1 squared. Judge me all you want. Okay, next thing I can do is say, well, secant x is equal to 1 over cos x. So maybe I will write this kind of laterally here, which is not really cheating because it is equal. 1 minus sine, oops, sorry, that's not supposed to be not another equal sign. It's equal to 1 over cos x times 1 minus sine x over cos x. Okay, and so that gives us this, that 1 minus sine x over cos squared x. Okay, because those multiply together and 1 times anything is itself. Over here, 1 minus sine x squared, well, remember, sine x, sine squared x plus cos squared x equals 1. That's our Pythagorean identity. If I rearrange that, I can say that 1 minus sine squared x is actually equal to cos squared x. So remember, 1 minus sine squared x equals cos squared x. Maybe I'll write in my steps here. And so I actually get that 1 minus sine x is divided by cos squared x. Oh, hey, look, they're the same thing. Left-hand side equals right-hand side. Okay, last of these that we're going to do, I'm going to break it down right in the middle right here so we can just get on with it. This looks like a quadratic, so kind of going to keep a wary eye on that one. And then over here, poof, we got a lot going on here. This is cubed. Disgusting. All right, so let's go ahead and let's do some work on a lot of these different things. Now, this one's kind of screams to me that there's going to be a lot of like bits and pieces that I'm going to have to handle. So we'll do one thing at a time and we'll see kind of what happens. All right, on top, I see a double angle identity here, and sine only has one. So I'm going to go ahead and I'm going to just replace that right now. So I can say that 2 sine x cos x minus cos x divided by, okay, and I'm just done with the top. So let's look at my bottom now. This is a difference of squares, right? 4 sine squared x minus 1. Those are both perfect squares. So I can break this down into 2 sine x minus 1 times 2 sine x plus 1. Okay, so that's nice, I guess. Ooh, actually very nice, because look, I've got this term in my bottom equal to my term over here. Delicious. Okay, so let's actually keep going with our left-hand side, because I know there's got to be something to get rid of that extra bit. And here's what I've got. I noticed that this cos x term is something that factors out, right? Both of those have a cos x in them. So I can do cos x times 2 sine x, and then cos x minus, or divided by cos x is cos x. So I have 2 sine x minus 1. And looky there, that is exactly the term that I wanted to get rid of. Okay, so I've got that and I can cancel it out. And I'm good to go here. Okay, let's go to my right-hand side here and kind of see what I've got. So over here, I recognize that both share a cosine term. So I'm going to go cos x. I'll factor that out. And so I get sine squared x plus cos squared x. And that all is divided. Oh, no. That was the worst quotient I've ever drawn. That is all divided by 2 sine x plus 1. Hey, I know this identity. This is the Pythagorean identity. And so I can go ahead and just say that this is equal to 1. And so I end up with this cosine x over 2 sine x plus 1. And on our other side, those canceled out. So I had cosine x over 2 sine x plus 1. And then I can say that my left-hand side is equal to my right-hand side. Woo! Now, the nice thing about you watching a video and me talking is that I can tell you exactly what I'm doing as I go over these. But the diploma does not have a record button, so you can't just speak nonsense into the paper and hope that the marker understands you. So what you will probably want to do, and by that I mean definitely want to do when you write your diploma, is instead of just talk through the replacements you do, you should do stuff like I did over here, where I make this little step and I explain, here's how I'm replacing this, here's what I'm doing. So make those notes along the side. I'm not going to do that in this video because you can hear me speak and because look at how hard it is for me to write things. I just want to get this over with so that you can get the ideas. You can hit rewind or hit the back arrow 50 times so that you go back in time and you can hear my beautiful explanations again. But you should be very explicit when you write this down. Remember, our diploma markers are wonderful people that hate you or something, right? There's some sort of issue they have with kids. I mean, don't we all? But they're vicious markers. So if you're explicit and detailed and careful, they're more likely to say, yes, you get marks. And if you just kind of breeze through things, or God forbid, you do a verification and say, there's my proof, they'll slap you with a 0 so hard you'll end up in, I don't know, whatever town you're watching this in, like 2 towns over, quite a ways. Okay, what's some more stuff we can do with our lives? All right, so I stole some questions from the textbook, and I think these are my last 2. Yes, they are. Excellent. Let's go ahead and let's solve these, and we'll say we're done. Excellent. So solve the equation sine squared x equals 1/2 tan x cos x algebraically and graphically. And my answer to the graphically part is no, you can do that. I don't need to draw you a graph. You know how to solve this. And hopefully also you can say, that's easy, I can solve that right now. Remember, if a multiple choice question is thrown at you and they don't say anything about how to solve it, just solve that thing as a graph. Life's good. For us right now, we're going to want to probably attack this with some identities. Okay, so my right-hand side doesn't look too bad. So we've got sine squared x is equal to 1/2 tan x cos x. I don't need to rewrite this whole thing, but I'm writing the left-hand side because I feel like that's not too bad. Our other side here, we've got 1/2. Well, tangent is sine x cos x. Okay, times cos x. Okay, so this one's interesting because check this out. These will multiply together. So we're just using that quotient identity, tan x is equal to sine x over cos x. And that gives us this, sine squared x is equal to 1/2 sine x. So maybe we'll do subtract 1/2 sine x equals 0. Because if we're trying to solve this and I see that squared, maybe I'm going to like do my my kind of quadratic trick. And in this case, actually, it's even easier because I can say, well, sine x times sine x minus 1/2 equals 0. Now I can use my zero product law, which says then that sine x can equal 0 and sine x minus, or sorry, I guess sine x equals 1/2 is just kind of an extra step, right? Because sine x minus 1/2 could equal 0, so sine x will equal 1/2. Okay, so now we're gonna get our answers. When is sine x equal to 0? Well, that's when the height of our triangle is 0. So that's at 0 plus minus. Well, they don't give us a range here. So yeah, we'll answer as a general form, I n, where n is an element of our natural numbers or our whole numbers, whoever, whatever. And then when is sine x equal to 1/2? Well, remember, sine is positive in our first and second quadrants. And that means that it's going to be at pi over 6, which is our short triangle in the first quadrant, and 5 pi over 6, which is our short triangle in our second quadrant. And for both of these, we can do plus minus 2 pi, where pi is, or we're 2 pi n, there we go, where n is an element of our natural numbers. Okay, graph, yeah, whatever, go for it. Algebraically solve. 3 cos x plus 2 equals 5 secant x. Okay, well, let's try this out. So we've got 3 cos x plus 2 equals 5 over, that's cosine x, right? Okay, so there we go. I'm starting off by giving myself the reciprocal identity. Now I'm going to treat this kind of like a rational, right? So I'm going to multiply both sides by cosine x. So I get this 3 cos squared x plus 2 cos x equals 5, but now it's a quadratic. So I'm actually going to bring that 5 over. So minus 5 equals 0. Okay, now this is one of those ones where maybe I'd make a factor diamond, but I ain't no quitter. So I'm going to go ahead and I'm going to try this without, and I should end up with 3 cos x plus 5 times cos x minus 1. There we go, equals 0. So I get that cos x equals negative 5/3 and cos x equals 1. Cos x can never be a greater than 1 or like higher in absolute magnitude than 1. So there's no real answer here, non-real answer. I don't remember what NRE stands for. And then cosine x is 1. Those are at pi over 2 plus minus 2 pi n, where n is an element of the not reals, naturals. There we go. Okay, so identities are nasty. Sorry, I'm not trying to scroll in. Scroll out, scroll out. This page, put a big, oh God, big gold star there, okay? Because the proofs section was a huge diploma written response last year. I bet you they do it again this year and every year. It doesn't matter which year it is. I bet they keep doing it because they're jerks and because it's hard. But eventually, if you keep practicing, maybe you'll stop thinking it's hard and you'll start thinking like me. It's a fun little puzzle to solve. Better yet, hopefully you don't end up like me. I have hope. Okay, anyone still watching, listening to this? Hopefully the rest of your studying goes well before your test, and I'll see you in your next course with me, which is probably nothing. Bye.